yeah. But from the musician's but from the musicians but from sound designers' point of view, from artistic point of view, we have got to the situation where I was almost technically kidnapped today. Can you imagine? Two guys in a bit desolated place just came up to me and started pulling me to the van. Had to argue a little, and maybe that's just a misunderstanding, but who knows? Who knows? Happens in Russia from time to time. And what I wanted to talk about in this video is FM and PM relationship. You can find in the technical literature that FM and PM are actually relatives. They are dealing with the same thing called angle modulation, and so they can be used to generate the same spectrum. But from the sound designer's point of view, having an FM or PM operator is not the same thing, especially when we have a complicated routings between operators. And the difference becomes even more obvious if we take the computational limitations, computational resources of our system into account. Because sometimes to make FM work like PM, we have to add some multiplications and additions, and the same goes for PM. So of course it's wiser to just use the one that suits the task better. And that's what I wanted to talk about in this video. So first, let's take a look at this PM operator. This operator has a sine-ask as a carrier signal. The modulation frequency specified as carrier frequency, which is a sweep, which goes from 60 Hz to 1700. Now I specify the range from 0 to value assigned to modulational index. It will be just 1. It's in radians, and it's not a rule to have it as 1. Probably it would be better to put it to pi, but again, that only depends on how bright you want the spectrum to be generated. So here it's just 1 because it works better for the comparison to the FM operator. And I shift the phase a little so that the modulation would start from 0. Yeah, so we go from 0 to 1 and then back. And that's all. Let's take a listen. So as we can see, the static spectrum just does the sweep and ends up on this saved to the memory position. Yeah. Now let's try to do the same thing with the FM. So as we can see, the difference here is that the higher overtones lose energy as the carrier frequency increases. In order to make FM in this case behave in the same way, same way as PM, we should have to add a multiplication by the carrier frequency. And once we add it to the modulational index, now we see that the modulational index depends on the carrier frequency. With PM, we have that for free. With FM, if we want that, we have to add it explicitly. Okay, it ends up at the same spectrum, but as we can see, as it goes through this sweep, the amplitudes of the spectral components change over time. Yeah, they get modulated. That's the thing that we get for free with the FM. In order to make a PM to behave in the same manner, we have to add an offset to the frequency. So I guess you can get the idea that by tuning these parameters or diving deeper into the mathematical formulation of FM synthesis, we can make them work just in the same manner. Yeah. Another thing is that if we would like to make PM to behave like FM, in this case, and lose high frequency energy with the rise of carrier frequency, we would have yeah, as in this example, we would have to map the modulational index to the carrier frequency, or carrier frequency to the modulational index. Yeah, as you can see here, we map this range of the carrier frequency to from 1 to 0.3, for example. It can be a different value, but so if we want to PM, in this case, behave like FM, we have to add some calculation and demand some resources from our CPU. This is not that important for the modern CPUs, yeah, but if we deal with something like those small what is they called embedded platforms here or something like that. I mean, those BeagleBone Bella and Raspberry Pi and so on. Then resources are very limited, so we should choose wisely which one we actually want. So with these two examples, I, for example, in most cases would choose FM because it behaves more natural and alive. I like this dynamic behavior of the spectral components, and I like that it loses high frequency energy with higher pitches. Sounds more natural to my ears. Yeah, another difference I'd like to point out is how they behave with a low modulational frequency. Here is the FM with low with fixed 100 Hz carrier frequency and modulating frequency of 10 Hz. Yeah, and here is same with PM. Now, if we want it to behave like FM above, we have to increase the modulational index. And so we get behavior that is closer to previous example. I increased the modulational index by 20. So in most cases, I would prefer FM to the PM. But there is also a case where I would choose PM over FM. And this case is cascades. Those cascades that I want to generate predicted, more or less predicted spectrum. Now I was asked about this algorithm from DX7 synthesizer. Here it is. TX7 is actually a phase modulating synthesizer. It uses phase modulation, not FM1. And the algorithm is as follows. We have two cascades. One cascade in which every previous operator modulates the phase of the next one. And I have to be clean here. I don't quite know whether it is added to the modulator of next operator or whether it modulates the next operator's modulator's phase. I don't know that, so I made just both variants. And another cascade is same as the previous one, but it has a feedback. Now we don't have, I would say like that, by default we don't have one sample feedback in Supercollider. For the computational efficiency reasons, we can set the control block to one sample, but that would demand more CPU for all the tasks. Yeah, so it was actually like that with Supercollider 2, if I'm not mistaken. You could play with the control block size on the fly, but then James McCartney removed that and made the third version where if you want single sample feedback, it's better just to do that in C++ and make corresponding unit generator. So actually we have FM7, yeah, that's the name, FM7 unit generator in Supercollider, and you can use that if you want the single sample feedback. Now I just made these examples with the default 64 samples feedback. I hope it doesn't differ that much from the one sample one. It should differ, but it depends on what is the modulational index, and probably might be an interesting instrument by itself. I don't know, I just made it, so let's take a look. So what we see here, this one is a phase modulational one. We have 6 lines. Every line stands for the one operator, probably a bit longer than usual lines, but it's good because we don't need that much scalability here. There are examples, if you want, you can search online. There are examples of the matrix, FM matrix, done in Supercollider language. They use some fancy array operations, but if you can do something simpler, something in a simple manner, it's better to do it just like that, because when you will come a month later and take a look at this code, you will faster get an idea of what you want it to do. But if you have some fancy loop that does something to arrays, maybe generates new arrays, maybe just changes the existing ones, then that loop has another loop inside and all that, well, might be good. Sometimes might be good, yeah, but sometimes just doesn't make sense. Well, one of the most important rules of any engineer, if you can do it in a simple manner, do it as simple as you can. Here, this is the same operator that was the previous one. The next one has a first operator as a phase input to its modulator. So the first operator modulates the phase of the next operator's modulator, and the output of this operator goes to the next operator's modulator's phase. The same goes for these three guys, with the only difference that the output of this cascade goes to the feedback and then modulates the phase of the first operator's modulator. That's FM. Now let's take a look, take a listen. Let's take a listen. Now the second example is the same as before, with the difference that every previous operator is added to the modulator of every next one operator's modulator, and they both, the sum of them, go to the phase input. They almost sound the same, but if we will increase the modulational index, we will see that the first variant, in which we have, I would say, a bigger cascade, because we modulate the modulator of the next operator, yeah. So in one case we sum two signals and they modulate one, yeah. This is not as rich spectrum as when we modulate one, then that modulates the next one's phase. So let's increase the modulational index. This is the first one, the richer one. And this is the sum of two modulators to the carrier signal. Yeah, I hope it's clean, but it's not that easy to explain that in a couple of words. So that's why I added these lines here, so it would be clean just from the explanation. Now let's compare that with FM variant, in which we do the same thing but with frequency. Well, we kinda do the frequency equivalent, but it will not sound as that at all. We'll just, if this was kinda very alike constructions, now we start doing a cascade with these same constructions. So let's compare the cascade, the same cascade made with FM. And now the one in which we sum the previous operator with the next operator's modulator. Now let's try with the bigger modulation index. This, the last one, is where we modulate the modulator of every next operator with this output, with the output of previous operator. It's more noisy than the previous one. So as you can see, when we start making cascades, we go far from each. As we start making cascades, so you can see, as we start to make cascades, the differences are emphasized much boldly, probably. If I would like to use cascades, FM cascades, to generate a very predictable spectrum, I would of course use PM for that. And I guess that's the reason why Yamaha engineers actually used PM, not FM, because it's cheaper. And FM cascades can also sound very nice. And here's the example. I will not explain how this code snippet works in this video. I leave that to people who are interested in that. But if you want me to do the explanation, let me know, I will do that. But for now, I guess this part of FM thing is covered enough for the musicians. We could go deeper with that, but I guess that's only relevant for the engineers. Yeah, and Supercollider is, in my view, is more a tool of composers and sound designers, who has to be engineers, but only to some extent, as much as it is required by their artistic tasks. Yeah, because we don't have infinite time and have to leave some place in our memory for artistic tasks, which are also demanding a lot. So that's it about PM-FM relationship. I hope this will be useful in your musical design. See you.